welcome to the application questions from Chemactivity 6A. So this is question 10. Let's read it together. Consider the following molecules for which Lewis structures are given. First, determine and draw the molecular shape. Determine the hybridization of the central atom, or the atom that I point at with an arrow, and draw the hybrid orbitals and any remaining p orbitals onto the structure. So here we've got carbon tetrachloride. That is a compound that you should be able to name. Determine and draw the molecular shape. So we've got carbon. It's got 4 regions of electron density. That tells me it's going to be tetrahedral. So if I draw that, I get this. If I want to now determine the hybridization of the central atom, I have to ask, well, what are the bond angles going to be? Well, they're going to be 109.45 in a tetrahedron. And that means that carbon is going to be sp3 hybridized. So I know how to draw a set of sp3 hybrid orbitals. They come in a tetrahedral shape, and there's going to be 4 of them. I'm going to draw a blue one going up, a green one going down, a yellow one coming out, and a red one behind. So each one of those is an sp3, and there are no remaining p orbitals on the structure. The question doesn't ask me to do this, but I can note that there is, because we learned about this in the activity, for carbon there's going to be a single electron in here, 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 and they're now, each one of these orbitals is now ready to form a bond. So we need to do that same activity for all of these. I'm going to go through and first draw all the electron geometries. So let's review what I've got. I've got water, has 4 regions of electron density around the oxygen. That's going to make it a tetrahedral environment. That means that the bond angles are about 109.5 and the oxygen is sp3 hybridized. So now I'm going to go through and do all the hybridization. In the case of HCOH, 3 regions of electron density around the carbon, angles of approximately 120, and that means the carbon is sp2 hybridized. In the next example, nitrogen has 3 regions around it. That's going to make the nitrogen is I don't know why I keep doing that, as sp2 hybridized. We can also look at the carbon, as we're supposed to do in problem E. Carbon also has 3 regions around it. That's going to make it bond angles of 120. And so carbon is, why do I keep doing that? Is sp2 hybridized. If we look at the last example, first we'll look at the carbon for example G. So the carbon has 2 regions around it. So going back to the Lewis structures, that means it's going to be 180. So that means the carbon is going to be sp hybridized. And the nitrogen, we haven't seen one like this, so we can also ask the question about the nitrogen. So the nitrogen, notice the nitrogen has a lone pair, and it has a region that is a triple bond. So we can say the nitrogen also has 2 regions, and so we can also say it is sp hybridized as well. Now, we want to draw the appropriate hybrid orbitals. So let's go back up to water. Water has sp3 hybrid orbitals. That means there's going to be a set of 4 of them, and they're going to be in a tetrahedral arrangement. One is going to point here at a lone pair, towards the bond, towards the bond. So in other cases, I was drawing each one in a different color. Now I'm drawing them in the same color. I've made it look like the lone pairs are bigger orbitals. They're not. I just wanted to make sure that everything fit there. So now we're starting to see another thing that hybrid orbitals can do, which we will learn more about in Activity 6B, which is they can also hold lone pairs. So let's look at some sp hybrid orbitals. On the carbon here, one is going to point in this direction, one is going to point in this direction, and one is pointing in that direction. And remember that there's a leftover p orbital that is coming out of the plane of the paper, so straight out at us. That same thing is going to happen here. Nitrogen is sp2 hybridized, 1, 2, 3 orbitals, and really the lone pairs are going to be inside. The lone pairs will be inside this orbital. And there is a leftover p orbital coming straight out of the plane of the paper. The carbon is also sp2 hybridized, 1, 2, 3, and it also has a p orbital coming straight out of you at the plane, on the plane of the paper. Finally, let's do this one in green. This carbon on HCN has 2 hybrid orbitals, one going along each of its bond or general regions, and it has a p orbital that's left that's perpendicular here, and then one that's coming out of the plane of the paper. The nitrogen likewise is sp hybridized. Notice its lone pair is going to sit in one of those hybrid orbitals, and it's going to have a p orbital going up and down and a p orbital coming out of the plane of the paper. These take some practice to kind of draw and to be able to visualize, but once you start to see how they work, it makes a lot of sense. And it will make even more sense when we start to think about how are these involved in bonding.